Okay. I didn't ask for the two parts. So what are the two parts of a compression wave? Since I didn't ask for it in the opening. We'll say it again, Alice, so they can hear you. A compression and a rarefaction. Okay? So you have to make sure you draw a compression and a rarefaction. Okay? That's what on your lab sheet or in question 3 that I said was missing on most of your pieces. I have to be able to see that. I can't just see a squiggle and you go, oh, that was my compression and that's my rarefaction. What is a compression? When they're close together. What's a rarefaction? When they're far apart. Okay? So I got to be able to make that out. So if you use a slinky, the loops have to be close together. And then the loops have to be far apart. Then the loops have to get close together. And then the loops have to spread apart. The loops have to be close together. The loops have to be far apart. Okay? That's a compression wave. Now, what else about the compression wave is different from transverse? It's what? It's flat. It's straight. Okay? It doesn't have that up and down. Transverse does that. Okay? So on your paper yesterday on the lab sheet, question 6 said, how are they different? I took 3 different answers I can remember. Okay? Which is, which one? What's the major difference between transverse and compression? Okay? The answers I took were, this one was parallel, and this one was perpendicular. That was the answer I was looking for. Okay? It's not the only one I took. All right? The other answers I took is the compression wave needs a what? Needs a medium. I took that the compression wave needs a medium. Oops, my U got a little messed up there. Does the transverse wave need a medium? No. So if you told me this one needs no medium, I took that answer. If you said compression needs a medium and no medium for transverse, I took that. And I took one other answer that somebody gave me, and I don't remember. It was only like 2 lab papers, so I'm pretty sure it was only one group. All right? This one has a crest, a trough, and an amplitude. So a transverse wave has a crest, a trough, and an amplitude. Do you have a crest, a trough, or an amplitude on a compression wave? No, because there's no up or down on a compression wave. So somebody said in a compression wave, there's no crest, trough, or amplitude, and there is in transverse. I took that also. But I only had that, I'm pretty sure, in one lab group. Yes, sir. I got one. Yep.
Do compression waves have energy?
Do compression waves have energy? Yes. They do have energy, and their amount of energy would be defined in how far apart that is. The further apart it is, the greater the energy. The closer it is, the less energy it would have. Okay, that's how their energy would be defined. Okay? Anybody else? All right, so we've done 1 and 2. So I drew the compression wave and labeled the parts. All right, is everybody okay with that's a compression and that was a rarefaction? Is everybody okay with how to tell them apart? You could say compression is parallel and transverse is perpendicular. Or you could have said compression needs a medium, transverse doesn't need a medium. Or you could have said transverse has a crest, trough, and amplitude. Are we okay with those 2? All right. Number 3. What's the difference between a compression and a rarefaction? Compressions are close together, and rarefactions are what? Farther apart. All right, number 4 is a calculation. So we want to use what formula?
E
V equals F lambda. All right, so which one of these is wavelength? The V, the F, or the stick man? Stick man is lambda. All right, so what is the frequency? Okay, so times 5 and equals what's the velocity? So how do I solve for the stick man? Okay, so we're going to divide by 5 on both sides. So stick man equals what?
9.
9, and we get what unit? Meters, because we're finding a length. All right. What's a medium? Yeah, we're going to talk about this again today, because I know this is hard for a lot of people. All right, it's a state of matter. Okay, I don't even care if you say it's. Didn't I talk about that hood a little bit ago? It's not cold in here. All right, it's a state of matter. Now, if you put that the wave travels through, that's great. But if you just say a state of matter, I'm happy. All right, so give me 3 examples of a medium.
Solid, liquid, and gas.
Sure. Solid, liquid, and gas. Now, you could have said the floor, the air, water. You could have been more specific if you wanted to be too. When y'all get up and all rush out of here for lunch, your feet are going to stomp on the floor. Well, if you got in the swimming pool and swim around in the water, you create waves. That's a medium. Water's the medium. When we're talking, the air that our voices travel through, that's a medium. Solids, liquids, and gases. Yes.
Would glass and light bulb?
Yes. It would. All right. Now, look at number 7. I put 2 times up there, and it drives people crazy when I do this. And I want you to calculate frequency and period. Now, every time I do this, people go, Miss Wall, what time do I use? Look at all these heads down, and then people are going to go on the quiz. What time do I use? And I go, I don't know. All right. If you got to find frequency, how do we find frequency?
Count the waves.
Count the waves. All right. So how many waves do I have? All right. Over what's my time? If you count all 6 waves, 6 waves was way down here, right? So what's the time? It's 6 waves. Then you got to use the 2 because that's how far down you counted the waves. So the frequency is 3 hertz. Now, if you wanted to use the 1 second, you got to quit counting where? At the 3, and you would get 3 over 1, which is still going to give you the same frequency. Okay? You can use the 1. You just got to quit counting at the 1. Okay? But if you go to the end, you count all the waves to the 2 seconds, and then you use the 2 seconds. Does that make sense? Okay. So how do we find period? So it's 1 over the what? 1 over the frequency. So what's the frequency? So 1 over 3 is 0.33, and the unit is seconds. Period's a second. All right, you still got the worksheet I handed back from yesterday? Let's run through a few of those, because some of us had some issues doing those. The front side we did really well on, because we had practiced that the day before. But the back side, that was a little messier. It was not identical, but it was very, very similar. Might have been the same. I didn't think it was, but it may have been the same.
It's the same, just different letters.
Well, then we should have all done well if we kept the same paper handy. But, you know, you'd be surprised how many people did not get all those questions right. I had some people get almost every question wrong.
I had everyone right that I did. I know a Friday.
Because the parents are just so
I know the blank lines at the top were not all the same because there were 5 fill in the blanks at the top.
C and D for number 5. Some of them were safe with about the same.
All right. Make it a little bigger. All right. What's the highest point of the wave called? Lowest point? What's the wave that measures the amount of energy called? Amplitude. The distance from one crest to another is called the wavelength. There we go. The measure of the number of waves that pass a given point is the frequency. What's A called? What's B? What's C? And D. Good. All right, down here in number 6, we've got some waves. It wants to know what P and Q have in common. They can have frequency, or it could have said what? Wavelength. Okay, either answer. Because the space between the waves is the same, so wavelength is the same. Or you could have counted the waves. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So either answer is the same, frequency or wavelength in that case. But P has twice the what? What's bigger in P? Amplitude. All right. In B, waves Q and R. All right. R has the same what? Amplitude, but R has twice the what? Wavelength. C, wave what has a steady frequency but a changing amplitude? T, wave what shows a steady amplitude but a changing frequency? S, and waves what and what have a low amplitude but a steady frequency? Okay, questions. Now, the back caused a few more issues for us. All right. So in A, is this wave longitudinal or transverse? Longitudinal. It doesn't go up and down. All right. Letter H represents a what? Are they close together or far apart? They're close together, so it's a compression. In I, are they close together or far apart? Then it's a rarefaction. All right. Letter G is showing you a what? It's showing you a wavelength. Now, a lot of you had trouble with that at the bottom of the page. They gave you the answer right there. But how do you know it's a wavelength? The definition for a wavelength is the distance between two corresponding points on adjacent waves. The waves have to be side by side, and they have to go from the same point. Look at where the point is, and look at where the point goes. It's in the middle of the compression, and it goes to the middle of the compression. Everybody see that? Middle of a compression, middle of a compression. So, 8 through the pictures created huge issues. So let's talk about how to get those. One day I'm going to be able to pick up a calculator with that hand again. All right. So a kid is playing with a swing. 6 complete to and fro's in 30 seconds. Calculate the frequency. All right. Now, what's the formula to find frequency? 4th period kept telling me it was V equals F lambda. Did they give you frequency, velocity, and wavelength there? No. So they wanted you to fall back on frequency equals the number of waves over the time. How many waves did they tell you you made? They told you made 6 complete waves. How much time did it take you to do it? 30 seconds. Now, if you left that for me, I gave you credit. A couple of people reduced their fraction wrong, and I marked it wrong. All right? You should have taken your answer and changed it to 0.2 hertz. I was even so kind I did not take off if you forgot your unit. Now, from there, you need the period. How do you find period? 1 over frequency. So 1 over 0.2. So 1 divide 0.2, and you get 5. All right, from there, these bubbles cause more issues in both classes. All right, we want to find period. What's the formula to find period? Period is 1 over the frequency. What did they tell you the frequency was? 1 over 440.
See, the wording about that. I got it right. The wording about that.
0.00227. And I took it out several decimal places, but you didn't have to. Again, I didn't take off for the unit. Now, the next one causes issues, and I'll be the first to admit that. Okay? This one reads funny. If you And several people in fourth period who got it told the other folks, read it really slow. All right. A marine weather station reports waves along the shore that are 8 seconds apart. The frequency of the waves is therefore how many hertz? The time is what? How many waves are there in 8 seconds? Every 8 seconds, there are how many waves? Every 8 seconds, there's one wave. So there's one wave in 8 seconds. So you say 1 divide 8. 0.125. That's the only one I think is hard on the whole paper because you really have to pay attention to the wording. Everything else, they just sort of give to you. All right, number 12. In what type of wave is the vibration perpendicular? Transverse. What type of wave is parallel? You could have said longitudinal or compression. I took either answer. What type of wave is produced when you have the end of a horizontal, has compressions or rarefactions? I jumped one. Longitudinal. When you have a horizontal spring and it goes up and down. Transverse. What type of wave has a wavelength? Both, or all types of waves. I wrote that on a lot of papers. And number 17, I said draw it. You could have drawn it anywhere. Okay? But basically, you have to have a wave that you can start and stop at the same place. So if I go to the end of the compression here, I draw my wavelength so it ends at what? The next compression. So that's a compression. So the next compression would be here. If I choose to go from, let's say, a rarefaction, I'm in the middle of the rarefaction, right? The middle of the rarefaction. Okay? I just have to start and stop in the same places. Questions about anything on the paper? Anything bothering you before we do the quiz? Okay? Yep. I'll give it back to you. Pick up my desk over there and I'll fix it while y'all do the quiz. All right. If you will, you need, if you want the formula, you can have your formula sheet or I'll just write it on the board. But you need something to write with. You need a calculator because I think there are, let me look. I think there's 2 calculations. I can't swear to it, but might not be in it. Yeah, there's 2.
You said you was gonna put the phone on the board.
Maybe you making it up?
Not saying anything about,
I'll be fine. Logan, you making it up? I need to take the hood off. Oh, what?
It's teaching on my eyes. I have one teaching. There's something like that.
There's something stuck in your eye?
Yeah. Like a piece of wood.
They can't take it out.
They tried to. It's in the bag. Like, I don't know how to. It did this weird thing. White, and they said that's in it. They can't get it out.
You want construction?
Why don't you go to the eye doctor?
It was in the wrong. I told her that, and she said no. It doesn't help.
Why don't you just go on, take the tweezers, go in the mirror, open your eye, and it's not bad. It's gonna hurt.
Formula. Yeah, there was something I was supposed to do. All right, there's the math formula. If it goes to sleep, just tell me and I'll stick it back up there. wrong with you? You don't have something right with either? How y'all planning to make it through a day at school with nothing right with? What's wrong about? Give it here. You better not put my calculator back in that box.
I was gonna ask the same question.
Oh, there's a missing letter. It's my fault. I forgot.
I was gonna say, where's it at?
Right.
F is missing.
Where's it at?
F is missing. How many crests do I have?
1, 2, 3.
Make it look right. Since I don't have it in front of me.
Here, I got you.
Here, let me see it, so I get all the letters in the right place. But I know F is missing. It's supposed to be here now that you show me the graph.
Is B even anything?
I'm not going to tell you that.
That's it. That's it.
Okay, yeah.
Thank you.
The letter that's missing on your graph at the bottom is F. That's the thing that's missing. Okay, so when you get down to the bottom, F is missing. Make sure you draw it in. Here, it's all fixed now. Like this.
You're so good.
In that case, you can put it up after the quiz and give me mine back. Thanks. Welcome. Yeah, I'm sure right here, so I need to give you a ruler. It's actually how you knew, but I'm not confirming that's correct.
So you're not gonna tell me if it's wrong either?
No, I won't tell you to try to work it wrong. You need this for 1920, by the way. Yeah. Huh? How many millimeters or a centimeter? 10? And if you've already done like John did on 19 and 20, he drew the lines, just put it back and measure them. Since I asked you to actually measure them. And as long as you're pretty close, I give you credit on those. You just get that back in front of me. man. You can set them on my desk, I guess. Just make it stacked over there. Thank you, ma'am. Thank you. Hmm?
Would Kieran, Kelly, Rajah, please come to guidance?
We're done. Be patient. There's just a couple people working. All right. Was that the last paper I was waiting on? I'm thinking it was. All right. If you still have a ruler, if you will, bring it up and put it on my desk, please. Leave those here so I get them for the period. All right, you can put your calculators in the tub too, because we don't need calculators either.
Take your message.
All right, Landon, put your calculator up, put your phone up.
That's so true. Oh, okay, you see that?
I had to remember.
Put the one up that you put on my desk and leave me mine.
Somebody took my calculator.
Miss Rock, I went to the bathroom.
You got any hall passes left? You're willing to serve detention?
That's clear.
Bree, you didn't do detention
I
yesterday.
gotta do it today.
That's fine. Remember, you need to do it while it's cold outside and I'm inside. Before you're dancing around yelling, you gotta go to the bathroom and I won't let you go. Caleb, remember, you're still on my list too.
What?
Detention for the bathroom.
You taking notes?
Uh-huh. All right, there's two things I want to talk about again that were just on the quiz. All right. Now, on the quiz a second ago, all right, I had a wave, and I had two parts. I don't remember the letter, and I had amplitude. We'll just make this A and this C. I don't remember what the letters were. I may even have the right letters. All right, which one of those is amplitude?
See.
It's C. A lot of you guys, as I watch the papers come in, put A. A is not amplitude. C is amplitude. A is two amplitudes. You got to go from the rest line up or the rest line down. This would be two amplitudes, so A is wrong. Okay, you can't pick A. Now, in looking at you guys measuring your wavelengths, some of you guys were all over the map on that second one. The transverse, where you had labeled and drew, looked pretty good. But the compression wave, again, you can pick any point. They just have to match the point you go to. So if you pick the front of the compression, you go to the front of the compression. Okay? If you pick the end of the compression, you go to the end of the compression. If you pick the middle of the rarefaction, you go to the middle of the rarefaction. The points have to be the same on each thing, okay? You can't start in a compression and go to a rarefaction. Does that make sense?
Yeah.
Okay. Because I saw some of those come in and I'm like, ooh, we've missed the boat. All right. So we're going to talk about mediums and EMR today, and then you're going to work on a scavenger hunt for the lab tomorrow. So, what determines the speed of the wave? Oh, and I'm picking the groups tomorrow, by the way, just so you know, because they're larger groups. What determines the speed of a wave? Anybody know? What?
Energy. Medium.
What? Yep. Okay, the medium the wave travels through. Okay, the medium affects the speed of the wave. Now, what affects the medium or the speed of the wave? Well, there are four things that affect the medium. One is the state. So we have four states of matter. What are four? We're not doing plasma. I've left my mind alone. All right, what are the three states of matter that we're going to do? Okay, so if we're doing solid, liquid, and gas, tell me, which state of matter do you think it moves fastest in? That's usually the answer I get. It's not right, but it is the solid. Okay? I know. People always think that, but it's not. All right? Let's see. Red's good enough. All right? Solids are greater than liquids. And then they're greater than gases. Basically, it is. Okay? They're the fastest in solids, and they're the slowest in gases. So, when, I don't know, you probably talked about this in American history, maybe not. All right? But when the Native Americans would hunt for buffalo, how do they find the buffalo?
They feel the ground shake.
Running, yeah.
Exactly. Okay. Now they could also track with paw prints and things of that nature, but for the most part, they could feel or hear the ground shake. Now, sometimes they just got lucky. They wandered up on a group of buffalo grazing. That was really convenient. But did it always work that way? No. All right. Those of you, most of you are probably not deer hunters. All right. But out in the county where I live, a lot of people are deer hunters. Well, if you're a deer hunter, what do you do all day?
Sit down and wait.
Sit down and wait and pray some poor unsuspected deer strolls by for you to shoot. Okay? Well, we can debate that later. Okay? But the part about deer hunting is you got to be patient and wait on some poor unsuspected deer to stroll by. Did the Native Americans have time to wait on a herd of buffalo to stroll by? No, they starved to death. All right, so they had to find the buffalo. Well, they could listen and sound would travel through the air. Well, air is not the fastest way for sound to get there. That's right, because the solid, the ground, is a much faster way for sound to travel. Okay? Sound travels better through a solid. Does that make sense?
They just like lay on the ground and say, oh, I hear it.
Secondly, I shouldn't tell you all this, but have you ever tried to listen to somebody's conversation on the other side of the door?
Yeah, put your ear up to the door.
Sound travels better through a solid. You can even put a glass on the door and work better too. All right? Not that y'all should ever try to come home and listen to somebody's conversation.
I'm about to.
All right? Now, what about density? We've talked about density this semester. How does density affect a medium? Do you think something that's more dense or something that's less dense would travel, a wave would travel better in it? Okay. All right, let me give you an example of something. Let's say syrup, like molasses. Everybody knows what syrup or molasses is, right? I don't like molasses. It's yucky. It's really, really thick syrup. All right, versus like water. Okay? So molasses is going to be more dense.
It would be.
All right, and water is going to be less dense. Which one do you think the wave would travel better in? In that really thick molasses or in the water?
Molasses.
The water, okay? The wave is going to move better in the water. So,
Isn't it because solids have more circular waves than alcohol? Is that why?
well, it's all got to do with the concept of elasticity, which I'm going to next, and that's the reason. Waves travel faster in less dense materials. It's got to do with elasticity and being able to return to your starting position, which is the one I'm getting ready to do. So you travel better in less dense materials. So like if you tried to make a wave in syrup or water, it'd be much easier to make a wave in water than it would be syrup. I know this is a stupid question, Logan, but how is it you got a piece of wood or a stick or something stuck in the backside of your eye?
He was in the woods and a stick hit him in the face.
Because I was gathering wood for a fire,
That's the best.
and it was on a, I think it's where the wood was on top of the branch, and it pulled up, and when I pulled it off, it came back and hit in my face.
It's Logan. That's the way. That's the best way to answer that. It's Logan.
Yeah, that's me. Always getting hurt.
Okay. So what did the hospital tell you to do for it? Other than sit there with,
Yeah, well, actually, put water on it, so.
and it's supposed to eventually come out?
Slide out.
Okay.
I don't know about that.
Okay.
They supposed to, I don't know.
Blink a lot. No work.
Okay.
Look down and start blinking.
Is it like in the eye or just like resting behind the eye?
Like, resting behind.
Like when you get something stuck in your eye, it goes to the side of your eye.
Okay, so it's not actually, it hasn't actually punctured the eye.
No,
It's red, it's like, it scratched it, but it hasn't.
Okay,
It's on the surface.
okay.
I want to see
All right.
It is red.
Okay. All right, so waves move faster and what? High temperature or low temperature? High temperature. Okay. Anytime you have a higher temperature, things are going to move faster because the particles are already doing what? They're already moving out faster or slower? Faster. Okay. Okay. Anytime you have a higher temperature, it moves faster.
So how does that work with phones?
Huh?
So how does that work with phones? Like the waves, like,
Like the signals?
no, like with the sound waves be faster and phone than it goes to a solid.
I'm not sure I understand the question.
Okay. Would it be faster, the waves be faster going from phone to phone or from me to right? That's solid air.
What?
Huh?
The waves are going through a solid when you're talking to a phone, right?
Okay, you explain it to me.
You know how you were talking about how the waves go. It works better if it's going through a solid, like when you put your ear on the door.
Yeah.
He's saying it's. He's saying would it go faster if y'all were on the phone because the phone is a solid, or would it go because y'all talking like that?
Yeah.
Like go through like the telephone, the waves.
Two different types of technology. If we're talking on our cell phones, it's traveling through the air. It's not traveling through a solid. How's it going to travel through a solid? Our phone is not physically connected to you. Is it? I mean, yes, I'm talking and I'm holding a solid, but once I'm done here with holding it, it's got to leave and travel through the air in some fashion because it's not connected by solid from other than that box from where it leaves there to get to you. Okay? So from that sense, it is left and it's got to travel through the air at that point. Okay?
What about cup phones? That make it.
A cup phone would be a solid because it's going to travel through a string. All right. Old phones, back when we first got telephone service, back way back in the, I don't know, when did that start? 30s, 40s, 50s, somewhere back in there. Back when they had cords, they had to literally unplug a cord and plug in a cord on. Y'all don't ever remember this unless you've seen old TV. Okay, where they lit. No, this is before y'all even had landlines. All right, but back in old TV. All right, my husband actually remembers this. He's 55. But when they had to make long distance phone calls, you had to dial an operator, and they connected you to the city you wanted to talk to. There was somebody who sat in an office in Thomasville, and they literally unplugged a cord and plugged in a cord to the city you wanted to call to make a long distance phone call. Okay, when you called to make a long distance phone call. Okay, I know that's a little prehistoric, but in that sense, there were actual phone lines that the calls transferred through. So that would be a little more like a solid. So it was still slow compared to what we have now. But now it's literally just traveling through the air with radio waves. Okay, but the technology is so much more advanced than that would. We can't even compare it to that technology, because that technology is like seriously antiquated to now. I mean, this is supersonic compared to that stuff. Okay, I mean, have y'all ever even seen rotary phones where you have to?
Yeah.
I have one at the house.
You have one at the house? Okay. I mean, most people we have one, but it's in the closet in case the other phones die during a storm. We can plug it into the wall to be able to punch the buttons, because ours are wireless, that have the answering machine, cordless. That's the word I want. They're cordless phones. Cordless phones don't work if you lose power. So if you want to make in our house, and reporting power outages are tied to our house phone. So we have to have something to call the utility company with to report the power outage. So we have to keep one in the closet to plug into the outlet.
So then how are you going to use it if the power's out?
Because if it's a landline that's not a cordless phone, it's not based on electricity. I just have to plug it into the the wall jack, that's the phone jack, and punch the button. It doesn't use electricity. Yes.
My grandma has in the antique cabinet. She's got one of those phones that.
Yes, that would be more along the line of plug in the thing, call the operator, and somebody would. And before that, you shared lines. So you would literally pick up the phone, and there might be somebody talking on the phone line, and you had to wait on them to get done so you could share the phone line to call somebody. And it might have just been across town. Yeah, I mean, we've come miles since then.
I'll have at least you gotta wait until they're done.
You got to wait on them to be done with their conversation. When cordless phones first came out, there weren't very many frequencies. And so you could pick up your cordless phone and listen to the neighbors talk. You used to be able to turn on your, baby monitors. You used to be able to turn those on and hear your neighbors talking on their cordless phone. Because all the frequencies were the same. There were only like 5 or 6.
I bet you people were weird and stuff.
I mean, so it was bad for a while there. You had to be careful of what you were talking about. You never knew when you were broadcasting on somebody's baby monitor.
I'm really trying to listen to that conversation.
So now now you just got to worry about the government listening to your phone call. All right. So elasticity. What's elasticity? Y'all know what that word is?
Flexibility.
All right.
And how far it can stretch.
Think about underwear. Okay. Everybody, well, if you don't wear underwear, I don't know about it. I just want to pretend that everybody's got on underwear. All right. So elasticity is essentially the ability to return to a starting position. Okay? So we all get up in the morning, take a shower at night, take a shower in the morning, whenever. If you don't bathe, I won't know that either. Okay? Put on a clean pair of underwear. We wear it for 12 hours, 24 hours, whatever our normal bathing procedures are. We get done. Oh, they're all stretched out. Throw them in the laundry. Get washed, pull them back out of the dryer, and voila, they're all back into their normal shape. Right? Now, after a while, what happens to them?
They're just stretching out.
They're stretched out. We decide, oh, they're trash. We throw them out. Everything loses their elasticity at some point. Okay? So, materials that are able to go back to their starting position are better able to allow waves to travel. So, which materials are able to allow waves to travel the best?
Solids.
Solids. That's why solids allow sounds to travel better than others, because they're more elastic. Okay? Solids are more elastic. All right? So they're better at allowing things to travel through them. Liquids are the next best at being elastic, and gases
are the worst.
Are the worst. All right? They have the poorest elasticity. So what? Well, they're molecules, and remember back in middle school when you drew pictures to show where the molecules were? Let me draw the circles. And you showed them like being close together, but they were able to move around each other, but they weren't really, really far apart. Yeah. That's what I mean by elastic. The particles are close together, but they're not super, super close together, and they can slide and move around each other. Whereas a gas, the gas particles are really, really far apart. Okay, so they're the least elastic. They're so far apart, they don't have to get anywhere near each other. So that's why they allow the least, or the waves are going to be able to move the slowest in the gases, because they're the least elastic. But the solid, their particles, if you look at those, they're in fixed positions. So their particles are the most elastic, because do their particles really move out of place? No, they're already in their positions. So they're going to be the most elastic because they're where they're supposed to be all the time. So sound travels through them very well. Or really any kind of wave. It doesn't have to be sound. It's just one that everybody can relate to. Yes, exactly. Yes, Logan. Yes. Try not to injure yourself getting it. And I will try to poke your eye out trying to get a drink.
No wonder it's in the eye.
All right. The second thing we want to talk about today, you really need your orange cards for, because we're going to learn to read one of the two things left on your orange cards. One is with naming compounds, and we won't do that until close to right before Christmas. And the second thing is the chart at the very bottom of the orange card. Okay, so find the orange card. You cannot do this without the orange card. Mr. George is still under the desk over there. I keep asking people not to throw your card away. Eventually somebody's going to take it, or I'm just going to throw it away because I'm tired of it. What's he going to keep with your stuff?
No, I just gave it to him and I forgot to get it back.
Oh.
I think it was after a quiz.
What happened to y'all's?
John took mine.
Right. Okay, so we're going to talk about electromagnetic radiation. We can abbreviate this EMR if you would like to, just to make it a little shorter on our writing. Okay? EMR is electromagnetic radiation. But basically, it's a form of energy. And it travels through space. Now, if it travels through space, does it need a medium? No. No. So these things can come from the sun. Hello, Lewis. How are you? I'm good. All right. Now, we need to be able to read electromagnetic radiation off that handy-dandy chart I just told y'all to pull out. Now, if you look at that chart, what are some examples of EMR that are listed on there? Look at the bottom of the backside.
Microwave, radio wave.
All right, so hold on. I don't take shorthand. All right, microwaves. I heard radio waves.
X-ray.
All right, I heard ultraviolet. I didn't hear anything beyond that. I was too busy writing. What? Gamma rays. What did you say, Alize? Infrared. All right, so ultraviolet, gamma rays, infrared. All right, all of the things that have been written up here, we can't see any of those. All right, we can look at the microwave all day long. We might see steam. We cannot see a microwave. Can't identify it. We can look outside and go, oh, that's a 102 jam signal? No, it's not. 107.5? 100.5? Nope. Cannot make them out. Nope. Not any day of the week. We cannot make out an X-ray. I could have stared all day long at that machine in my busted up wrist. I was never going to identify an x-ray while I was sitting in that hospital room. All right? Ultraviolet. Ms. Thornhill was in here yesterday when I was talking about ultraviolet. It'd be really cool for her AP Environmental Science class if she could look up at the sun and say, oh, that's UVA. Oh, that's UVB. We cannot see any of those. So what is the only thing on that spectrum that you're looking at that we can see?
Visible light.
That's correct. It's got a little tiny section, and then it's pulled out at the bottom. But the only one we see, all right, the only one we see is visible light. And I've got some other stuff on it in a few minutes. All right, now, how do we tell the difference between all of those? How do we know if it's gamma, which is a form of nuclear radiation that can cause cancer, and none of us want to be overly exposed to, or if it's going to be a microwave that'll be safe to heat our popcorn, which is what most of us probably use a microwave for, is reheating and popcorn. All right? Maybe some of y'all actually cook food in it, like cook a meal with a microwave, other than reheating and popcorn.
Yes, sometimes. I mean, there's some things that I can see stuff.
Okay, all right.
I cooked some of them.
Okay, potato and bacon. Okay.
Bagel bites.
You know, but I always wonder, does anybody ever buy like chicken and actually cook chicken in the microwave? Okay.
I've unthawed chicken in the microwave.
Okay. So, how do we know the difference between infrared, radio, and visible light? No, we can't. Look at your charts.
You can see the light.
All right. It has wavelength. Now, our chart only gives us wavelength. So that's how we're going to tell the difference. Now, some textbooks give us the opposite of wavelength, which is what? It was on the quiz today. What's the opposite of wavelength? Frequency. Our chart does not, because the state wants you to know the relationship between the two, so you have to know the difference. So, what's the relationship between frequency and wavelength? They're inversely proportional. What's that mean? Okay, so you see on your paper how it says short wavelength?
Oh my God.
I'm sorry. And then it says long wavelength. All right. What does that mean for frequency? Because the state wants you to know that and be able to translate it.
This short low frequency.
Okay, so where it has long wavelength, it means what?
Low frequency.
Okay. Low frequency. And where it says short wavelength, that means what?
High frequency.
That means high frequency. Because they're opposites of each other. Short means high. Long means low. You have to make that translation. Okay? So that's why the state does not put frequency on our chart. Because they want you to know this relationship and come up with that on your own based on what we've done. Does that make sense? Okay. Does everybody have what they need? So, if you look up here and the state says which has the lowest frequency, and you have choices of X-ray, UV, IR, and microwave. They want you to be able to read this based on what we just talked about. Okay? So does your chart show frequency anywhere on here on exam day? Does it say frequency? Does it, Alexis? Got a phone. All right? Does not show frequency. It shows wavelength. Longer. What's the opposite of longer? Short. Let's say low. All right. Opposite of short. That's how you read the chart. Now, I already answered this one. What's the only type of EMR we see? All right. Now, what if they want to know something about the order of the colors? How you know the order? All right. Anybody know the way to know the order without that? I always ask, and so many people have no idea what I'm talking about when I ask this question. Logan. Why do you suppose I'm yelling at you? You're smart enough to know because you just put it away. If you have an eye injury and you can't look up here and pay attention to me, you should certainly not be on your phone. Then listen with your eyes closed, not your eyes on your phone. Does anybody know what that means?
Red, orange, yellow, green.
Have y'all ever heard of Roy G. Biv?
No, I don't know why I can't.
Nobody's ever heard that before? All right? That's how you know the order of the colors. All right? Roy G. Biv is just the order of the colors. All right? It's the order of the rainbow colors. The only color that people always struggle with is I. What's I stand for? Yeah, it's the really, really dark blue. Okay? So red, orange, yellow, green, blue, indigo, and violet. But Roy G. Biv is just a way for you to remember the order of the colors. It's a mnemonic device that I'm always surprised people don't know. It's like when you learn to convert metrics, maybe in elementary, middle school, King Henry died by drinking chocolate milk. Any of y'all remember that one? Yeah. You remember learning the lakes for Lake Michigan, Lake Huron, Lake Ohio, or Holmes, Huron, Ohio, Michigan, Erie, and Superior. Or the lakes around Michigan.
No, the math one. That's another one.
Okay. Those guys, forget it. Apparently I'm the only one that learned that. Now, what determines whether we're going to see blue light or green light or red light or what's on the chart? What do them numbers stand for? It's on the chart.
Oh, measurement in meters.
What are those measurements in meters called?
The wavelength.
Very good, Jacob. It's called the wavelength. I told y'all it's on the chart. Okay, in big bold letters. What's it say up there? It is. But remember, that bottom part, they just blew it up because it stands for that little skinny part in the middle of the chart. Okay? So it stands for the same thing. So if I ask you what color has the longest wavelength, what color has the longest wavelength?
Red.
Red. Okay? What color has the shortest wavelength? Violet. Right? All right.
Isn't it true, whatever color something is not the color, like that's only color it reflects?
It's got to do with that, yeah. It's been a long time since I've taught that, but I think what you see is what is reflected, and what you don't see is what's absorbed.
Color, like this isn't black. This is like every other color but black.
I think so. Yeah. It's really weird the way that works, but I think that's correct. All right, let me see, because we're ready to do the computer work, and it's 1:10. And I don't want to do the computer work with it being 1:10.
So what you trying to say?
This isn't orange. This is every color but black.
Which is what we need to do.
So you're saying every color but black?
All right, I guess we're going to work on this for a second.
Every color.
Every color, but color.
And what if it was all different colors?
Color box going on.
If it was yellow and green and blue, y'all be good. We'll be good.
We could be aliens.
That'll be good to come to school, everybody different colors. Now, that's embarrassing.
When I first heard about that, I was like,
All right, I want you to answer those two questions real quick. Don't yell out the answers. Give everybody a chance to read the chart.
You see it? Where'd it go? Is it something? Stop.
I'm gonna go home and go to sleep. Not in my bed. He had all of that.
All right. So what'd you get for which color has the lowest frequency? All right. Again, does this chart show frequency? No. So long wavelength means low what? Frequency. This means high frequency. Okay. That's where people struggle because they look at this and they automatically see long, short for frequency. It's not. It shows wavelength. So you got to remember they're what of each other? They're opposites. So short means high frequency. Long means low frequency. So which color has the lowest frequency?
Red.
Red. Okay, we good with that one? Now, the second one, I just asked for longest wavelength.
Red.
So that should be pretty easy. I said which type of EMR. Okay, so type of EMR would be what? Stay up here, not in the colors,
Radio wave.
but radio waves. Okay, are we okay with that? Any questions? All right, I'm not going to get out the computers with 6 minutes left. So we're going to do the scavenger hunt tomorrow and the lab tomorrow, which means we will review Friday, which puts the test where? Test's going to be Monday. Okay, I know you don't like Monday tests, but there's just nothing I can do about it. Calculators are back. If you borrowed one of my sheets, put it back. If you still have a ruler at your desk, put it on my front lab counter, please.
Let's go.
If you have makeup work you need to do, I'll be here today. Next week, I could only do Tuesday and Wednesday. I forgot Thursday, I have a meeting that I completely spaced.
Right.
Yeah. Well, it's not a whole day. I mean, I count minute for minute. So you just sign in for the minutes you're here, and I add them up towards your 90. Okay. And you guys need to put your butts in a chair.